properties of chiral systems. And
Thank you. Thank you, Mr. Chairman. And let me thank the organizers and Axel in particular for giving me the opportunity to speak here in this meeting. I'm sorry I have a very short time in Stockholm this time, so I didn't have time to follow the meeting up to this point. I will not be able to follow it very much. In the future, I'm leaving very early in a couple of days, and there's a lot of things to do. It's always nice to be around this place. I have to be very careful because I once said that it's always nice to be here in Stockholm, Spain. And I've been at times giving Spain to Norway in my presentations. Stockholm to Norway in my presentation. At times I make mistakes in my presentation, so I present it as a country which is different from the one it is. That's because I'm traveling a lot. So I don't know where it is. Like said,
yes, we are. Today is Thursday, and you are in Stockholm.
Thank you very much. Okay. I don't see the...
Oh, did you send the signal? Oh, you're not even connected.
Yes.
How's that possible?
Good idea is, before I start, I can see, and you can see what I want to talk about.
Are you sending a signal?
I think I am. Should we just...
function key and this one or something like this. Yes, that's it. Now it should work. This is the way it should be.
Should we wait?
No, now it's too long. Strange.
Yes. Can we?
Oh, now you need to resize. Resize in there. Oh, yeah, I think that's best.
Resize.
I mean,
No.
put the right size, of course.
It's not a matter of just moving it a little bit.
That's not the problem here.
No, I think
But I could.
you are missing one part of the right side.
You could, of course, try and do the reset button.
Depends of you.
Are you sure? Yes.
Yes.
It's coming. No. Let me see that.
It's big at least, but it doesn't. I think your size, the screen is simply too big. Need to get through. Oh, yeah.
Yes, it's not exact.
You know what I mean? If you go to the background.
Go to the background.
Yes.
Now I am sort of lost here, you know? It happens. Function.
Escape, first of all.
Escape, first of all, right? See?
Oh, no, I don't see anything. Neither here nor there.
Well, probably I should have asked before about...
Yes, there's a mouse. Do you have a mouse?
Yes, I do.
I mean, even this doesn't work.
This.
Or maybe now it works. This one, yeah?
Yes.
Uh-huh. Right. So how do you make it get out of this? I mean, I want the background. How do you put it in the background?
Let me do that. I think I am starting to understand what you mean. We can start going out.
And then you do...
No.
Normally you would have background here when I put the right hand. Yeah, here we go.
Yes.
Properties, yeah?
No.
And then of course, is that settings?
Yeah. Impostazione is setting, yes. Okay.
So that's it. Alright, and then C?
Yes. That sounds good to me. And we go back.
At least it's not Japanese, it's even harder.
Okay, sorry for that, but okay. Well, what I'm going to talk about here is the ab initio calculation of linear and nonlinear properties of chiral systems, and so it's going to be the results of sophisticated calculation on properties which are linear, like one photon CD or electronic CD, and two photon CD, which is something which has been we started to study only a couple of years ago, 1 or 2 years ago. Then I'm going to talk about magnetochirality, which is a subject on which very much has been done by Professor Buckingham. Professor Barron was in the audience. And then, if I have time, I'll talk about classical and optical Faraday effects, also on chiral systems. Let me go, since we have lost some time, let me go to the first subject, which is 1 and 2 photon circular dichroism. As I said, this is something we started to do, in particular, 2 photon circular dichroism rather recently, and it's a collaboration which is now involving a lot of people, and as I said, now I think Stockholm is in Sweden, Lund is in Sweden, so everything is okay here apparently. It's something which we started with this student, this postdoctoral student in Pisa a couple of years ago. Now he is in Aarhus. Then it's a collaboration with Hans Ogren and Ilo in Stockholm. Thomas Mondo Pedersen, who was in Lund, now I guess is working and making money for a firm in Denmark. Benoit Champagne in Namur, Susanna Monti and Patrizia Santoro in my institute in Pisa, together with Nalin, who is a PhD student from Stockholm and China, visiting Pisa. Kenneth Rudd in Tromsø, Maxime Guillaume in Tromsø, and then some other, Xiang Zhao, Ji Jingling, and Sui Zhu from China. So a long list of collaborators for different parts of this work. We are talking mainly about 2 photon circular dichroism, and dichroism is a change in the imaginary part of the complex refractive index after interaction or radiation with matter. So you have the difference between the imaginary part of the refractive index for left and right circular polarized light. In particular, 2 photon circular dichroism is a process in which you have 2 circularly polarized photons. Actually, one of them is the circular polarized, the other can be pretty much everything. Interacting with a system, with a ground state and the final state, you have the difference between the absorption that you have when the 2 photons, or one of the photons is right polarized and the other is left polarized. So this is something which has been first described by Pinocchio in 1975, I believe. Also Power and Andrews have been working about this property in the 70s, and the derivation of the expressions that Pinocchio and Power and Andrews have been doing for 2 photon absorption is this circular dichroism is an extension of what you get for 2 photon absorption. When you see the expression of 2 photon circular dichroism, you can see that if, of course, it has to be a dichroism if the difference in the absorption, if you take into account only the electric part of the interaction, would be 0. There is no difference. It has to be something which involves the magnetic field and the quadrupolar magnetic interactions and quadrupolar interactions. So the difference in absorption for left and right, apart from some constants and some functions of the frequency of light, will be a combination of terms. In particular, 3 terms here, which with molecular functions that we call B1 Ti, B2 Ti, and B3 Ti, combined with some numbers, B1, B2, and B3. So it's 3 terms. B1, B2, and B3 describe the dependence on the polarization and propagation parameters, and this is a table taken from the paper in 75 by Pinocchio himself. You see that B1, B2, and B3 are very simple numbers, integer or fractions, and the numbers change with the setup of the experiment. So if you have 2 left circularly polarized photons parallel to each other, you have this number, and so on and so forth. And this is telling you that you can have several different experimental setups that give rise to photon circular dichroism. And concerning instead these quantities, the molecular quantities, which depend on the frequency B1, B2, and B3, we call them Ti because we use directly the approach, original approach by Pinocchio, who's using the velocity formulation for the interaction operators, so that we can get something which is by default origin invariant by construction. Since we have magnetic fields around in quadrupolar operators around, this is an essential ingredient that we can get something which is origin invariant. And these quantities are in particular a combination of tensors, and the tensors are MP, PP, P plus, in this case, for two-photon circular dichroism. Tensors which have the typical expression of the two-photon absorption tensor, so there are some of the excited states of operate matrix elements of the operators between the ground and the excited states. And the operators are the velocity operator, this is mu p is the velocity operator, then the magnetic dipole operator, and then we have this PR plus. PR plus is the velocity version of the quadrupole operator, so it's something like 1 over 2 PR plus RP. If you use these expressions here, in this form of tensors, which as I said is what Tinotto did originally, what you compute is always independent of the completeness of the one electron basis set. It's always origin invariant, and you have the guarantee that when the basis set becomes infinite, you're getting to the exact result. Here I also report this tensor, which is the classical two-photon absorption tensor, S, which involves instead a summation of the excited states of matrix elements of the electric dipole operator. And this allows me to connect two-photon absorption and two-photon circular dichroism. The expression of two-photon absorption and dipole approximation and for the two frequencies which are equal to each other is given by this expression here, very similar to the previous one. There is again a combination of fundamental units, and in this case it's only the S vectors, the S tensor, which is involved in the combination. And you can see that the F and G and H quantities are again numbers that take care of the polarization and propagation conditions, and they are related to the numbers we had previously given for two-photon circular dichroism. Now this is all that I'm going to say concerning how we do it, because behind this there is of course a lot of work done in particular by the Scandinavians, in particular by the groups in Stockholm, here in Aarhus, in Tromsø now, in Oslo, to develop a modern analytical response theory. Because what we can show easily, what can be shown easily, is that the tensors that are important for two-photon circular dichroism are actually second-rank tensors, and they can be obtained as single residues of quadratic response functions. This is the typical expressions we use for the residue of a quadratic response function. This is a quadratic response function with frequency omega c and minus omega b. And if you take the appropriate residue of in particular these 4 different types of response functions, then you can get all the tensors computed at a given omega. And nowadays, again, thanks to the efforts of a lot of people over the years, in the last 20 years in Scandinavia and in other parts of the world, you can actually compute these things with an extremely high level of accuracy, also for very large systems nowadays, because now we are going towards linear scaling approaches for calculations of electronic properties like this, not only at Hartree-Fock level, but also multi-configuration Hartree-Fock level, with several hierarchies of coupled cluster models, which means really sophisticated calculations for relatively small systems, or density functional theory, which is, of course, what you want to do when you have big molecules of interest in biology or in nanotechnology, with an extremely high level of accuracy and also computation in a very efficient way. Moreover, since most of the systems that you are interested in are in dense phase, nowadays with the coupling of modern response theory with a polarizable continuum model, which is PCM, by the way, a property, a model which has been developed essentially in Pisa by the group of Tomasi in Pisa. The coupling of the two things allows for calculations made without high accuracy also in condensed phase. Since I'm also going to talk about one electron circular dichroism, this has been known for a long time, I also mentioned the relationship with one photon circular dichroism. is two-photon CD can be written in terms of this rotational, two-photon rotational strength, combination of three parameters. One photon circular dipole, or ECD, electronic circular dipole, can be computed if one can compute this rotational strength, where you have to compute the scalar product of these matrix elements between the ground state and the final state. And this is the pictorial description of what you are doing here experimentally, measuring the difference in absorption between photons going circular polarized left and right. So we can also compare the two spectroscopies and see what is the advantage of one with respect to the other, one photon with respect to two photons. When we started, the first thing we did, we went for all natural proteinogenic amino acids. There are 19 of them. They are all, these 19 are all chiral, and we went in and we computed the 1 and 2 photon CD spectra and 2 photon absorption spectra with the lowest 6 excited states for all these natural amino acids, the chiral ones, for neutral gas phase molecules. We computed the excitation energies from the poles of the linear response function. You can show easily that if you can compute the pole of the response function linear, you get all the excited states, energies. And then from the single residues of the appropriate quadratic response functions, as I said before, you can get all our tensors, and so you can go on. These are the details. We used to use P3LIP, which for, as I heard yesterday also, from someone else who was giving a nice defense in Stockholm, it's used now by almost 80% of the people doing calculations in quantum and in computational chemistry. So it's extremely popular, and we've in fact started with P3LIP in this study, a basis set of correlation consistent basis set, which is quite we can prove it's quite adequate for our kind of calculation, in spite of the fact that we are using a velocity formalism. When you use velocity formalism in this kind of calculation, you have to be very careful with the basis set because of convergence problem with respect to electric, to the use of the electric dipole operator instead of the velocity. But we can prove that this is extended enough. Then these are also some other kind of details, which, and I stress, it's calculations we can do thanks to the existence of this nice program, Dalton 2.0, which has been developed by a lot of people in Scandinavia. So this is a comparison between the electronic circular dipole spectrum and the two-photon circular dipole spectrum of phenylalanine. This is vertical transitions. So if you have for each electronic excitation, you have a nice Lorentzian here, which we have with alpha with alpha 8, which is 0.1 EVs. I'll discuss about this a little later. At any rate, you can see that these two have different frequencies. Of course, this omega is half of this because this is the two photon, this is one photon product, but the states are the same. And as you can see, the response of individual states here can be quite different. So we have very big peaks here. We might have either transparencies or no response whatsoever in the ECD spectrum. So the two spectroscopies are quite complementary, and they can be used in fact both to help in fingerprinting the different type of amino acids. And this is what I'm saying here. In some cases, the TPCD spectrum is opposite to the 1CD. We can ask, and we've been asking ourselves, can we measure this? Now, if you look at the expressions, and you will take the ratio of the two-photon circular dipole towards the absorption, you see that we have something which is proportional to the ratio of the rotational strength with a 8 over C0 here. So this is quite, it's a term which is reducing a lot. Of course, we expect something much smaller for the dichroism with respect to the absorption, and you can see that for tryptophan, for instance, well, the factor is a factor of 1 over 300, more or less, which is what was expected, between 1 over 100 and 1 over 300, so 2 to 3 order of magnitude smaller. but still it is in the range of things that we can measure, because now with some techniques like modified Z-scan techniques, it looks like they can measure ratios of like this of the order of 2 or 3 to 10 to the minus 3. So it should be detectable, but as I keep repeating, it should be, because it's never been seen yet. So I hope that sooner or later, to convince the experimentalists to go in and try to do it. One of the ways is to improve on our approach and the quality of our calculations. For instance, we know that the amino acids have a lot of conformations, so they are big molecules that they can stay in the gas phase and in the solvent phase, where they are preferential, by the way, when you make measurements. You have a lot of configurations. So what we did, we started improving on our calculation for the amino acids. There is the group of Zijing Li in FA. They've been consistently publishing a lot of papers with the structures of amino acids in the gas phase. For all of them, take 100. There's 19 amino acids. There's hundreds of conformations in the literature. So we asked for data from the group in FA, and we started to do calculations in the gas phase. This is, for instance, an example of what you can see if you do something like this. You take 10 conformers, the 10 lowest conformers in the gas phase, 2 photon circular dichroism, and you do the calculation of the spectrum in this region between 1.7 eV and 3.1 eV, and you have here the different curves for the different conformers. Of this, only the black one, this one, is the one which has 54% of percentage Boltzmann averaging. Boltzmann percentage is 54.4, then you have 11.1 for conformer 4, and so on and so forth. But you see, what you get is this heavy line here, once you Boltzmann average over all conformations. But you have to take into account that this conformational variety is extremely strong, and this is true also for natural optical activity, for other properties like this. Conformational analysis is fundamental, because whatever you get for one conformer can be completely put upside down once you start averaging between different conformers. This is actually a good case, because if you look, well, yeah, this we can skip easily, but it's more pictorial than any other thing. We did calculation with beta-lit, but nowadays we like very much cam-beta-lit, which is a modification of beta-lit with a different type of parameterization, which takes care much better, for instance, of the quality of the response of Rydberg states, and I'll show you a very nice example later on. And you cannot see very well, but here you have the 10 conformers and the final results. But maybe if you can compare one thing with the other, and if you had this in a larger screen, you would see that the difference between beta-lit and cam-beta-lit are very high. So people doing beta-lit calculation of these things, message is be very careful, because beta-lit might be completely off. You're worried about basis set, you're worried about the geometry, etc., and you just have the wrong functional for this type of properties. Cam-beta-lit.
This is the neutral tryptophan, you say?
This is neutral tryptophan.
And if you take Peter ion and you take the other one, they act differently?
Of course, we didn't do this in this case. We did it in another study for vibrational response and natural optical activity, things like that. But we didn't take this into account. But there's even more. This adds even more complication to the.
But what is the concentration of the neutral tryptophan in the vapor phase?
This I don't remember.
Because this is under the assumption that all the molecules are in the neutral phase.
Neutral, sure. Yes, but then you should put in the Zwitter ion terms. I agree with you. Get this into account and complicate even more the picture. I agree with you. This part is not taken care yet. We did it for infrared, but we didn't do in this case. Just to tell you how complicated these things are. This is in vacuum. I'm going to the solvent in a moment. This is still gas phase, and you have solvent here, in fact. And I have displaced the abscissa here, so that the two coincide. So you see that if you go to beta-lit and cab-beta-lit, and this is the same abscissa, not only the spectrum changes completely, but it's also shifted a lot. Camber lip has this very nice characteristic, especially when it's Rydberg, it gets it right on top in most of the cases we have seen. Whereas bitter lip can be quite off. And you see that this is ECD, by the way. I'm not showing it anymore to photon CD, because this very recently we started to see that even for ECD we can get a lot of improvements in our calculations going to a better functional. And you can see that anyway the complication of these systems, the fact that the spectra can change a lot by simply changing the quality of the functional, and I tell you it's much more important from what I can see than basis set. This is for tryptophan to photon CD. After all, comparing still at bit lip level. This is a comparison between one conformer and 10 conformers. You see that the changes are not huge, but there is still some change, and the intensity of this peak is shifted and is increased, just as a combination of effects of the different conformers. So it's something extremely interesting. But I want to go to some other cases here where we have also added interest and added complexity, and also one case coming later where we are comparing this experiment. One study we just got published with Hans Open and Benoit Champagne is the study of helicins. Helicins are nice systems with helical structures. This is a simple 6-member ring helicin. It has some added this is sulfur, some sulfur atoms, and this sulfur and oxygen, so we add them complications here, but it's all helical, and so we expect that these systems here have a response which is stronger than the other systems we've seen before. This is structural chirality we are talking about. In fact, indeed, look at the hexahelicin, which is the first one. Sorry, I'm going the wrong way. Well, let me see how I go back here. It's this one. And you can see here from the comparison of two photon CD and two photon absorption, not only that the spectra, that the response of this state, for instance, is much stronger in dichroism than in absorption, but also that this factor is not 1,000 or 100, but it's 10. So the photon CD of hexahelicins, it's comparable, or much more comparable with the absorptions. These are systems for which the measurements of 2-photon CD might be easier with the techniques we have here. Here I'm showing different results for the spectra in 2-photon CD, 2-photon absorption, and ECD. The main purpose of this is that we have a problem here in these calculations, and it's how we treat, unless we had Barbonic or we do something more sophisticated, how we treat these peaks. We just assign Laurentian with a 0.1 EV, half width or half 8, and you see that if you just change this by a factor of 1 order of magnitude, the spectra changes completely. So this is totally arbitrary from the point of view of the theoretician. We need information on this, and we need to know how to treat this thing here, except, that this also comes partly from Barbonic coupling, so we have to add. Otherwise, you can see that the spectra look very different, but they are the same spectra, just using a different Laurentian for each peak here, a factor of 1 different. So this is a comparison with experiment. It's not very exciting, mostly because we miss vibrational structure, but also because most of these experiments are done in solvent or in some other condensed phase. So we do have this comparison. Also, we were asked by a referee to put this comparison in, but of course we have some of the features, like the negative peak here, reproduced, or some of these peaks being reproduced, but we still are a long way before we get to a comparison with the experiment for helicins. Nevertheless, they have strong response, so they can be used to measure the potency of the dichroism. This is probably the best case I can show you from my point of view. This is 3-methylcyclopentanone. It's a small molecule, but for this there is a study by the group of Bob Compton in Tennessee. Bob Compton measured a resonance-enhanced multiphoton ionization CD in this molecule, which is a 2+1 photon experiment in which you tune with 2 photons to an excited state, and then you ionize from that excited state, and you do this with a circular polarized light, so you can measure dichroism for this 3-photon system. This is as close as you can get up to this point to a real experimental measurement of 2-photon CD. And he did this measurement, but he was puzzled by some of the features of his spectrum. A year later, then he published with this group also a study of the effect of solvent and temperature on the distribution of conformers. We met at a conference in Crete, and he was very excited about the results I was having. He asked if we could do something, so we started doing calculations. What we did was we took the 2 major conformations of 3-methylcyclopentanone, which are known to be in the gas phase and in the solvent phase, the equatorial methyl and the axial methyl conformer. We took these 2 and we started doing calculations for all properties on this, a ECD, 2-photon CD, and 2-photon absorption. You can see here where I have the equatorial and the axial. This, in the gas phase, it's mostly 90% equatorial and 10% axial. You can see that the strength is pretty similar, but this being 90% larger is the one giving the feature to the Boltzmann average spectrum. This is not true for TPCD instead, since the axial has a stronger response with respect to the equatorial. But I want to go on further. We did a very complete study on this. First, we studied the level of optimization of the geometry of this molecule, because in this different conformers. So we went in, we optimized the different conformers in the gas phase with different basis sets of increasing size, and you can see here that practically you cannot see, except for the highest excitation, or in this peak here, you cannot see any difference. So the effect of geometry on this spectra, whether it's 2-photon or 1-photon, is not very large. So we can we can be sure that the geometry is not influencing our results. This is a very nice comparison, in my view, between the experimental ECD spectrum taken by Compton and the ECD that we compute. If you take Bitrlip, if you take Bitrlip, Bitrlip is the red. You see that you have this big peak here, which is pretty much around this band. This band is vibrationally resolved, and this is a typical excitation to a pi star, and pi star excitation, broad, and pretty much the two approaches get the right position. But then you see that Bitrlip has the next peak here, instead Bitrlip has the peak here, and this is the experiment. So we are exactly on top of the experiment for this Rydberg type of states, which we can identify from the orbital analysis exactly as being NS and a combination of N3S and N3P fixed. You can see that Bitrlip is off by 20 to 30 atomic units, and also the intensity is a little stronger. And then you have the next peaks here, which cannot be seen by experiments. We are already at the point where we are living in the area where the experimenters can work with 1-photon CD. So this is a very, very nice comparison that we have with experiments for this system. One of the reasons why we did this calculation is that Bob Compton had seen a different sign for this state here, in particular, this peak, this N3S peak, between one photon and 2-photon dichroism. And he had seen a different sign. He was puzzled by that. Now we can say with extreme good accuracy that the 2 states actually here have the same sign. Give the same sign for the circular dichroism. You see that the red and the green are giving the same sign, but when this is so strong, in this case this peak is very small compared to the next one moving. So in the experiment where you have a broader enlargement of these peaks, then this peak actually gets dissolved in the other peaks, and so they see a different sign for the transition. So I think that when Bob will see this paper, which has been sent for publication last week, he will really be very, very happy with the results that we are having. We can do, as I said, things in the solvent. I have similar pictures also for 2-photon CD and TPA. As you can see, there is a choice: benzene, chloroform, chlorobenzene, tetrahydrofuran, methanol, acetonitrile, and water. This is only a choice of solvents. He has made measurements in more than 30 different solvents, and we can see that the effect of the solvent is very small on this peak. Once again, an N pi star type of peak, which is, by the way, negative. This is the equatorial. This is positive for the equatorial and negative for the actual. But as a result of the Boltzmann averaging, is positive in the average. But there is a big complexity with the different kind of solvents here. And this is worth another kind of experimental analysis. Now I want to get some complexity into this. I want to include vibrational structure. And the way we do it, we use the linear coupling model, which is also partly, I guess, work done in Stockholm a few years ago. If we take vibration into account, then we can put here the symbols for the electronic and the vibrational states and around matrix elements. You should tell me when it's enough. Still. The harmonic approximation, this vibrational states can be written as a combination of one-dimensional different modes, and then the Born-Oppenheimer approximation, the matrix element. This matrix element can be written in terms of an electronic term plus an electronic term, and the matrix element of the vibrational state of this electronic matrix element depending on the normal coordinates. And this is a straightforward Taylor expansion. This is very straightforward, so I'm not going to go into detail, but you can see that you can have a first order term which is related to the geometry at the equilibrium, and then the effect of the remaining terms. And the same you can do for magnetic perturbation, and then when you have the result, you can plug it in the rotational strength and then a vibrationally resolved rotational strength, and then the observable, which is the anisotropy of the molar absorptivity. In the linear coupling model, what you do is the excited state and the ground state, you assume that they are mutually displaced and they have the same curvature, and then you can write things in terms of a Frank Condon contribution plus an Elsbeth-Teller higher order contribution. This is what we did for 2-photon absorption. We did it also for ECD. And this is, you cannot see it very nicely, but this is, because this is a small picture, this is red. I hope you can see that there is some red here and some black. And this is what we compute as a Boltzmann, as a combination, of the Frank Condon and Elsbeth-Teller profiles in the Bitterlip and in Cambitterlip level. And if I blow up this, which I will do in a moment, you will see that the experiment and theory are practically on top, one of each other. This is Boltzmann averaging over two different conformations, Frank Condon, Elsbeth-Teller, one on top of the, combined together in the gas phase, and we go one on top of the other. This is the same profile with what we compute, what the experiment has. So a little bit difference in the experiment, some shift here, a little shift which we can explain, but then we can also have individual assignment. Let's say that this, for instance, is a peak that comes from transition from the ground vibrational states of several modes. This is a peak that comes from the 0-1 transition in mode number 35, and can see exactly all the different modes and resolve this spectrum almost perfectly. You can see that this peak here, these two peaks are exactly at the experimental frequency. I don't think that this is, I think the effect of cancellation, I think that this is a very nice, well-behaving molecule, probably, but I think that it's not very easy to find this kind of agreement between an experimental and a theoretical ECD spectrum. Okay, now I want to move to another subject, which is most likely to be the last subject of my talk. I will not have time to talk about Faraday effect. And this is a subject which is very, very well known to Professor Bowden sitting in the audience, because he is the one who wrote the theory for this effect, magnetochiral birefringence, in this very nice paper. I believe it was 1983 with the Vantage. paper which I've been reading and reading all over again several times, because he was not only talking about birefringence but also about dichroism, and we are going to do dichroism, calculations of dichroism very soon. Well, we started doing magnetochiral birefringence a few years ago, and it was something I was doing with Paul Jorgensen, Sonia Coriani, Michal Jarzynski, and Magdalena Petzel, a collaboration between Denmark, Norway, Italy, and Poland. The results we got at the first time were very controversial. We had problems in getting into the literature because they were conflicting with experiments. So we went in, we did it again, we sort of confirmed these results, and now I think we can say that it's the time the experimentalists go in and refine their results. Let me show you, and let me see if I can convince you. Magnetochiral birefringence, what is it? You know that natural optical activity is present in molecules without improper rotation axis, and the Faraday effect, which is present for all molecules in a static magnetic field, they can be observed only for polarized light. So you have to have a polarized light in order to observe natural optical activity if you have chirality around, or Faraday effect, which you observe in every kind of fluid. You can observe it in vacuum. There are, in fact, there's people, I would say my brother has been working also in these things in vacuum, or in the effect of parity violation on Faraday effect in nature, which is related to homochirality. So I find a mention also homochirality. There is a third order phenomenon, it's magnetochiral activity, which may also be observed for non-polarized light, and this is magnetochirality. It's been predicted for chiral systems in a slightly magnetic field. Believed that, as I said, Baron was one of the first to predict it. Baron was certainly the one who wrote all the theory. And
I didn't predict it, unfortunately.
No, it was Bogdanova, was it?
I developed a usable molecular theory.
Yes, but it was Bogdanova who was...
Yes, it's a bit obscure, the origins, and the stuff is Russia somewhere.
Yes. In fact, it's in there, but the theory is here. The theory is I can tell you, is Baron and Verbanjic. So if you have an external magnetic field which is collinear with the direction of propagation of the light beam, so magnetic, I'll show you a setup in a moment. You have what is called axial anisotropy, axial birefringence, and this is an anisotropy of the refraction and of the absorption indices, so you can have magnetochiral birefringence, which has been measured, magnetochiral dichroism, which has been also measured in Toulouse by Gerd Ricken in this great lab. And what we are discussing now here is birefringence. This anisotropy changes sign when you change the sign of the magnetic field and of the light beam. Of course, we could go into all the symmetry, beautiful symmetry aspects of this. And again, I refer to the papers and the book by Lawrence Baron for these things. It's treated, well, I shouldn't say more. It's fantastically treated in his book and his papers. And the fact is not circularly differential, it does not depend on polarization of light, but for the same experimental alignment of magnetic field, the induced shift differ in sign for the two enantiomers. So it's been discussed at some point in connection also with enantioselective photoresolution and enantioselective synthesis, where you just use the magnetic field to get an accumulation of one enantiomer in a racemic mixture. It's been discussed in connection with this kind of experiment a few years ago. This is the kind of experiment. What you have to have, just to summarize, you have to have your light, which is polarized. This is the way I try to say it's polarized. Then a magnetic field, which is parallel. And it can be parallel or anti-parallel. So experimentally, this is a very tricky thing to measure. Extremely tricky thing to measure. And it's the same setup of Faraday then. But of course you need, in case of Faraday, this is polarized, it's linearly polarized, and you only have one magnetic field. Moreover, this is a chiral sample for magnetochiral birefringence. Whether if you have Faraday, it can be anything. So this is a setup. It's been measured. It's been measured by the French group in Rennes, and before that by the group of Barnier in Zurich, I believe, yes. No, what we did was we went in, we computed this axial birefringence for molecules like carbon, limonene, and proline. I don't have the structures here, but they are rather nice, quite large, not very large, but things that you see is 20 to 30 atoms. And they were studied at the FT bit lip level. Previously we did at the FOC, we included the effect of the condensed phase with the PCM level. We did Boltzmann averaging over the few lowest energy conformer, and we compared with the experimental data. And the data obtained by two experimental groups, that is the French group in Rennes and Georges Vanier, were already in disagreement with respect to the magnitude of the effect. They were in disagreement. By the way, they were both published. No, I think one of them published things in Physica Revue Letters, which is a high impact journal. It's the French published there. And the French published there saying we cannot reproduce the results by Vanier, but they got it published, Physica Revue Letters. Then we sent our paper, where we would disagree with both of them, to Physica Revue Letters, and they said, no, we don't want this theoretical shit. This is wrong. It's wrong by default, so we never got it published there. Okay. In fact, this is the approach, as I said, by Baron and Verbančić, who proved that this quantity, the actual birefringence, is proportional to a combination of two types of responses, which are both quadratic responses. One involves two magnetic dipole operators, one with the frequency and one without the frequency, and the other involves instead the quadrupole operator. So you can see that there is an effect of the static magnetic field in this last operator, which is with zero frequency, but you have to involve the chiral quantities in the molecule with the magnetic field and that quadrupole thing attached to the frequency. If you can compute these things, you can compute magnetochiral birefringence. For us, it was rather trivial when we did this, and this is, at this point, probably the last slide of this book, unless I really have some time, which I don't think I have. This is the magnetochiral birefringence per unit magnetic field and unit density, and for carbon and limonene, the geometries are optimized at this level. The temperature is 298 degrees. And we have several types of results here. For carbon and limonene, this is the Hartree-Fock number on the single molecule, minus 0.6. This is, if we go a little farther, we get DFT, a little of electric correlation. We just jump up to 53. Then if we add the effect of the environment, we go down minus 28. It's still the sign is negative. Then we average over the six lowest line conformers, we go down to minus 1.23. And if we do this at PCM level, it's minus 461 in the experiment. Vanier is 5,000. Okay? Then we go to the French experiment. We do Hartree-Fock at 16. With DFT 33, DFT PCM 35. We average. I said it's very complicated. Boltzmann averaging can do a lot. Do wonders. We change sign, but it's still at minus 36. And we settle with PCM at minus 33, and it's a order of magnitude with respect to the French. Now, you look at this paper here, the French paper, they do their own evaluation, theoretical evaluation. They use a simple dipole type of model, a simplified dipole model, and they get minus 28. So they are themselves in disagreement with their experiment by a factor of an order of magnitude, and they are very close to what we do. So we have everything inside. The point is, we can probably recover this. I told you that bit lip is not good. Now, after I've discovered this, I say, let's do it bit lip. I don't think we can change this, not even this, in order to get to minus 320, but this is one thing we should do. Basis set might be a problem. If you want, and I think it's mostly vibrational, some vibrational effects, we might get close to minus 320. So I believe in this experiment. What I think we never do is we get to this number. So there are two possibilities. Either the Baron-Verbančić theory is wrong, which we were discussing a moment ago. I don't see where. So if you, Lawrence, have any idea, just let us know. Or they simply measure something else. They probably have some spin, something around, or some other property. Because this can be wrong. And this, and with this I end, must be the reason why in this beautiful book on chirality Varnier published 2 or 3 months ago, in spite of the fact that he knows very well the story because we've been exchanging a lot of mail, he never mentioned our results. I think still in his book, it looks like this is magnetochiral birefringence you should measure. And I think that somebody should go in with the experiment and redo this experiment and figure out what's going on. I think that I said enough. I think I tried to convince you that we can do a lot of interesting things for these nonlinear properties, also with quite fancy and exotic ones. I know that parity violation, for instance, is something that's discussed a lot in connection with homochirality of light. There is a lot of work also in that field. I didn't do anything directly, but there are linear and nonlinear properties. As I mentioned, Faraday effect and the effect of chirality, or parity violation of that can also be discussed. Linear and nonlinear properties, they are all within reach of the quantum chemists. So I hope that in the future we can get more interesting results and improve on what we've been doing. Thank you very much for your attention.
For your presentation, I only regret that Spaghetti is not here, and
Yes.
the other one, because we could have a good discussion now, yesterday, and then we have questions, please.
When you do calculations on the mental complexes that Britain has worked on,
Yes.
I think it was a European complex, an effect transition or something.
You say no?
European complex.
In principle, I guess.
No, he made the first observation of magnetochiral dichroism a year or two before the Varnier experiment and the birefringence, and that's probably a much more sound measurement.
I'm sure about that.
Yeah. And then he went on to show the absolute enantiomer selection, because there's interest here actually in the magnitude of a possible enantiomer selection experiment with the magnetochiral influence. It would be nice to get some estimates actually of the sort of magnitude of the enantiomer selection you might get and how it compares with the use of circular polarized light, for instance. That would be a very nice comparison.
I'm looking at Silvinas right there, because we've been discussing yesterday with Silvinas doing calculations on an ytterbium complex for this NMR chirality things that Barakingham has been studying. It's been discussing a lot. It's been talking a lot about this effect of chirality in NMR, and this example was an ytterbium complex with high spin. Now this europium, from my point of view, sounds pretty close, but this is a frequency-dependent properties, and I'm not sure to which extent we can do these things, and Silvinas is probably going to start thinking
the
about
actual complex that Ricken used for his absolute enantiomer selection experiment, I think it was a chromium for settling down, I think it was chromium.
I think europium sounds to me more...
Well,
you said something, europium I remember.
Was the one where he observed the dichrosis.
Okay, the chromium.
To actually show the enantiomer selection, you had a slide showing these two complexes.
Yes, right, yes.
Yeah, I think it was chromium.
Yes.
So if you could do that one explicitly, we had the experimental data on it. And you could also maybe see what happens with circularly polarized light.
Yes.
You'll see
Yes.
impact calculation.
Yeah.
Yes, that would make a very nice
That's right, and I'm looking at you, and I'm at the same time looking at Silvinas, because the only person I know that can do this kind of things is we need help from him, because he has open shell. He can treat open shell, he can treat this kind of systems, and as I said, in the future I can see that whatever is done can be very much of use at this point. I remember when Ricken did this kind of things, because he publish it in Science or Nature or something? In Nature. So I remember talking to him over the phone and saying there is a lot of people outside my door. Journalists from all over France want to talk to me about this. I don't know what happened then, because it became very popular at the time. He was still in Grenoble when he did that, if I'm wrong.
About the very curiosity, the Boltzmann average, it is also calculated. They are reliable, more reliable. It's in the calculation. It is not possible an error in the conformation average.
Now, you're referring to this thing.
Yes.
This has been, as I said, a very controversial thing. First time we published this number, we really had the referee biting us. As I said, I didn't quite understand why experimentalists can publish a paper which is in complete disagreement with another experiment and get physical regulators, and the theoreticians cannot, because they're by definition wrong. So we had to be very careful about that. The Boltzmann averaging here is taken care with, I guess we did calculation of free energies at the DFT level, and nowadays this is not the problem anymore. So systems like this, it's not a problem. And then, at any rate, you can change the Boltzmann average as you want, but from this,
That is the sign.
forget the sign, but also the size. There's no way. It's too large, the disagreement here. And if I even asked the French to reproduce the number in Carbon using their simplified approach, a simplified theory, just to see if there is no error somewhere hidden in our calculation. But there is no way that you can go to 5,000. And this, I mean, I said before, if you look at the experiment, it's a very tricky experiment. This, I guess we agree, this is a very complicated.
Is your theory all right? Or?
I believe so. It still looks fine to me. I mean, when these results came out, I had another good look at it and scratched my head and didn't see anything wrong with it. I was going to ask, I mean, to give us confidence in your calculations here, what happens when you calculate an observable for which there are very reliable experiments, like the quadrupole birefringence experiment? Did you calculate that?
Yes.
How did that compare?
Yeah, within error bars always. I mean, I've been all my life.
So that was very close.
Yes.
And that was quite an exotic problem.
I think this is a good. Thank you for this, because I was not referring to these things, but it is, in fact, it was exactly the quality of our results for the Buckingham birefringence that pointed out to the fact that there were two different theories which were in disagreement one with the other. It was exactly the fact that we were on top of Buckingham birefringence with Buckingham theory and not with Raab that induced Raab to look into his theory.
And so your confidence in my theory that you're using...
I think that...
I've used it, it's a similar philosophy. I used the same for the Buckingham Raab calculation and got the same results as them, for which you have now, you say you computed very closely to the observation.
You see,
so it all sort of holds together.
There's so many things with the experiment that can go wrong, especially if the experiment is extremely new and you don't have any comparison. I'm just thinking that if you get these exotic properties like cotomouton or Buckingham birefringence with such a strong response by some particular species, if you just have a sample of neon, for instance, and do cotomouton measurements, cotomouton is magnetic induced birefringence. You simply have a magnetic field perpendicular to the direction of polarized light. Then you have an electricity building onto it. This is very well known, but if you do it on neon and you have a small percentage of argon there, and what they sell you is not 99 pure, and you don't go there for an exact analysis for these very complicated systems, you just get it all wrong. And it's simply because, and this induced me into a fight with my brother actually, because my brother measured the neon birefringence, and he got a number which was 1, and I was computing 5. And so I challenged the numbers by my brother, and he had to go back 10 years after to do the measurements, and he is now at 5 plus or minus 3. The error bars, the experimentalists have to put into their experiment is extremely important. And in fact, I point out to the fact that none of the experiment, the theoretic, this disappeared, but if we were still, well, in this table, you can see there is no error bar attached to the experiment. No, it's not, it's something happened. The experimental numbers, as I mentioned to you before, they have no error bars. So who knows? You know, in cotomouton, it's very often you see something like that. The electronic contribution is 1 plus or minus 200. What does that mean from the experimental point of view? That they can see anything. They can see whatever is possible. It's a very complicated experiment. Now, what is the error bar that Bagnier has in his experiment? If the error bar is 5,000 plus or minus 2,000, we are in perfect agreement. So it's too bad that he retired. But this group should be, I asked actually, his group should be following. There's nobody following this group. No, not that I know. Okay.
More questions? Well done. We have coffee break now. We thank you again.
Thank you.